Good afternoon and welcome to our live stream from the California Academy of Sciences Morrison Planetarium. My name is Ryan White. I'm Senior Director of Morrison Planetarium and Science Visualization here at the Academy. And I'll be your host for the next 25 minutes, half hour or so, as we tour the universe from Earth out to the cosmic microwave background. And although this is a program that for the last several months we've been doing as a simulcast from Morrison Planetarium every Wednesday at this time, we're actually switching it up a little bit. So for the next several months, the last Wednesday of every month, we'll be live streaming to Morrison Planetarium's Facebook page, as well as the California Academy of Sciences Facebook page, California Academy of Sciences YouTube, and OpenSpace, which is the real-time free software that we use to do this program, the OpenSpace YouTube channel as well. So last Wednesday of every month, look out for this program, and we'll have a different set of presenters all the time. And since it's not simulcast from the Academy, we have a little bit of freedom to answer questions. If you have a question that pops up, please feel free to put it in chat. And our producer for today, Ken Ackerman, will be able to pass that question along to me or pop it up on the screen, and we can see if we have time to address those. But I'm going to go ahead and disappear because the important image is over here on my right-hand side, and that is the image of the International Space Station, because that's where we're going to start our program. The International Space Station is a great place to start because it's basically human scaled. If you can imagine, from one side to the other, the ISS, as we like to call it, is about a football field in length, about 100 and some odd meters long. I'll prefer to use civilized metric units and try to mention the imperial units when it comes to mind, but 100 meters, 100 yards, about the length of a football field, or if you're European football, same thing. It's about the same size as a soccer field. So the ISS is as far as humans go out into space these days. It's a few hundred kilometers, a few hundred miles above Earth's surface. In this case, we're kind of looking down toward the Pacific Ocean and actually revealing some bathymetry as well, and some islands kind of coming into view in the upper left-hand corner. But as we travel around the globe and through our three-dimensional model of the universe today, it's important to note that we're using as much data-driven imagery as possible. So we're going to pull away from the ISS, the International Space Station. It kind of looks like it's plummeting into the Pacific. That's not the case. What's happening is we're moving away from it. And let me go ahead and add a line here. That represents the orbit of the ISS around Earth. So we pull away, the ISS gets smaller in our field of view, and we begin to see more and more of Earth's surface. And you'll actually be able to see that I think ISS just flew over Australia from our vantage point. So it should be showing up over on the left-hand side of this screen. And we're actually over the Pacific Ocean. We're now fading up a almost real-time view of Earth. This is what Earth looked like about a day ago. And you'll notice that there are kind of these bright seams that connect different parts of the globe. And there are even, here is a nice example of it, this kind of stitched together set of images. And what we've done is we've actually used satellite images of Earth to show you what it looks like pretty much right now, because we are still missing some of the data over the Pacific for today. We actually show you what it looked like about a day ago. So what's great about this is that we're getting a sense of how we use data in this visualization package, again, called OpenSpace. And it's sometimes kind of shows the limits of where we've looked in the universe or what we're able to measure in the universe, because our measurements aren't perfect. They're incomplete. And sometimes that's makes for some very obvious kind of changes to the way we depict the universe around us. So we're pulling away from Earth now, and I just want to bring up a couple markers to help us make sense of how we're traveling out into space. So far, we're traveling quickly, but we haven't broken any cosmic speed limits yet. Eventually, though, we're going to break the cosmic speed limit of the speed of light, which is about 300,000 kilometers per second, about 186,000 miles per second. And the best way I can think of to kind of give a sense of the scale is to actually use that cosmic speed limit as a measuring stick. It's something astronomers do all the time. You've probably heard of light years. Well, there are also light seconds. So the distance that light travels in a second, light minutes, the distance light travels in a minute, and a light year, the distance light travels in a year. Now, those aren't measurements of time. Instead, they're measurements of distance because it's how far light, again, the fastest thing in the universe, travels in the time that we mentioned. So here you can see the orbit of Earth kind of extending down into the bottom of the frame, and sort of encircling Earth is the orbit of our moon. Now, the distance from Earth to the moon is about 400,000 kilometers or 240,000 miles. And that's about a second and a half or so in terms of light travel time. So if you think about that, when you look at the nice, brilliant full moon in the night sky, you're seeing it as it was about a second and a half ago. And as we slowly kind of rotate around Earth at about the same distance to the moon, we're kind of passing in front of the constellation of Orion. If you're familiar with the night sky, Orion is an old friend, but even if you don't get a chance to go out and look at the sky much, Orion might be a constellation you can pick out. Now, coming into view, we have the sun, and that is kind of shown as an orange dot with a very bright halo in the way we're depicting things. And you can also see the traces of orbits of other planets around the sun. So we have Earth's orbit and the moon orbiting Earth, but then we have the 8 planets that orbit the sun. And again, for a measuring stick, remember that distance from Earth to the moon, about a second and a half. You can think of that as like sort of a brief pause in conversation. The distance from Earth to the sun is much, much greater, even though on screen it looks like less. I'll actually kind of bring us around to get a perspective that shows how far away the sun is. So the sun is about 150 million kilometers away, or about 93 million miles. And in terms of light travel time, that's more like 8.5 minutes compared to the second and a half it takes light to travel from Earth to the moon, or vice versa. So the light we receive from the sun, it's a beautiful sunny day here in San Francisco, that light took about 8.5 minutes to travel from the sun to Earth. And you can think of that as maybe a quick fast food meal. 8.5 minutes might be how long it would take you to really gobble down a possibly unhealthy rate, a lunch on a short lunch break. But you can now see the orbits of the 4 inner planets, or terrestrial planets, Earth-like planets. Mercury closest to the sun, Venus, Earth, the 3rd planet out from the sun, and Mars. Now, these are the planets that are most like Earth, which is why we call them terrestrial in our solar system. They're rocky. They have surfaces that you could imagine, at least with a well-equipped with a spacesuit, you could land on the surface of these planets and you could walk around. But there are other planets in our solar system that are quite different. And those are the next 2 planets you can see moving out from the sun. We have Jupiter, Saturn, coming into view, Uranus, and finally Neptune. Neptune is, to go back to our sense of scale here, the distance across the entire diameter of the orbit of Neptune's orbit around the sun is about 8 light hours. So it takes about 8 hours for light to travel from one side of Neptune's orbit to the other. So you can think of that as maybe a good night's sleep. So distance from Earth to the moon, second and a half, brief pause in conversation. Distance from Earth to the sun, quick lunch. Distance from one side of the solar system to the other, as measured by the diameter of Neptune's orbit, is more like a good night's sleep. And yet, and it's not in view right now, but the nearest star is about 4 light years away. So that's the difference between a good night's sleep, 8 hours across the solar system, the nearest star, 4 light years. That's more like a high school or college education. So light, fastest thing in the universe, takes about the same time it takes to get a high school or college education to travel from the closest star to our own sun to us. So the universe is truly vast, and in the few minutes I've been talking to you, we've already traveled farther than light would travel, faster than light would travel. And that's what we're going to keep doing, because as we go farther and farther away from our solar system here, we're going to get a broader perspective on the universe around us. Now, I've talked about light as sort of the fastest thing in the universe, but we've sent spacecraft out into the universe as well. The 5 fastest spacecraft we've sent out are the 2 Pioneer spacecraft launched in the early 70s, Voyager spacecraft also launched in the 70s, and the New Horizons spacecraft launched in the early 2000s. And so we're seeing these pop up slowly, but those 5 trajectories are now superimposed on our orbits of the planets around the sun. So these are the fastest nuts and bolts objects that we've sent out into space. And if I pull back far enough, now remember, some of these were launched back in the 70s. This trajectory here that extends, that kind of terminates before, inside the boundaries of the screen, that's the New Horizons spacecraft, which visited the dwarf planet Pluto several years ago. But these other spacecraft were all launched much earlier. And as we pull far enough away from our view of the solar system, we can see how far they've made it out into space. And I want you to just sort of visually estimate here, but you'll see, if you can imagine that, again, Neptune's orbit is about 8 light hours across. You can see that the most distant of these spacecraft, the 2 Voyager spacecraft, have traveled about as far as light travels in a single day. So they've been traveling for 50 years. Light, by that time, has made it well past the nearest star and to many stars that are relatively close by. But after 50 years, none of these physical objects that we've launched from Earth have traveled more than light would travel in a single day. So when we learn about the universe around us, we're really using light because of its high speed and ability to be collected by our giant telescopes in orbit around Earth and on Earth's surface. We're using light to study the universe around us. And that's because even with our sophisticated equipment that we've sent out into the universe, we've only explored essentially the solar system. As we pull farther away, those trajectories are going to kind of fade into the distance, and you'll see that the sun is going to get brighter. We sort of fudged the brightness of the sun compared to the other stars, and we're now making it the appropriate brightness relative to the other stars. So it's depicted the same way as the other stars in our field of view. And the sun is a fairly ordinary star. And as we pull far enough away, except for the fact that it sort of stays at the center of the screen, it's easy to lose it amongst the other stars in our relatively nearby in our galaxy. We've now traveled tens of light years from home, so the distance that light would travel in several decades. And we're sort of still orbiting the sun's position, so we can see the shift of the stars, so they kind of appear to drift across the screen. And then in the distance, you can maybe make out, I hope you can make out this sort of hazy band extending from the middle slightly to the left up to the upper slightly to the right side of the screen. That's actually our Milky Way galaxy seen from the inside. So we're looking at hundreds of billions of stars, so tightly packed, but so distant that their light kind of smears into this hazy, milky appearance. The dark bands that kind of cut through the Milky Way are actually not the absence of stars, but the presence of dust blocking the light from more distant stars. But in the foreground, all of these stars that are relatively close to home, we'll get another view of the Milky Way galaxy shortly, but all of these stars that are relatively close to home, kind of interesting to think about how many we now know have planets in orbit around them. And it turns out a lot. Each one of these circles represents not an individual solar system, but rather just it's a location marker to show each one of the stars that's in the center of each circle has evidence of a planet or planets in orbit around it. And you can see off in the distance, there's a very sort of large collection of smaller circles. Those are way off in the distance. That is a tremendous footprint of an observatory the Kepler mission from NASA, that observed a small part of the sky, relatively small part of the sky, and found evidence for thousands of planets. So I'm sort of circling it here now with my pointer, kind of just to the right of the center. So we know of thousands of stars with planets in orbit around them. This is a relatively recent discovery starting in the mid-90s. But this is a tantalizing kind of perspective because it gives us a sense that there are other worlds that are out there in the universe that are like ours. And it's intriguing to think about what life could look like perhaps on one of these planets, or just whether or not some of these planets would be good places to search for life. It's a puzzle that astronomers have worked on for many years, and it's an active area of research for astronomers today. But to flip that around just for a moment, we can also think about sort of if there were intelligent creatures on one of these planets from one of these stars, what if they looked back at Earth? Could they observe life here on our planet? And one way that we've looked for life on other worlds is by searching for radio signals. This is an effort that started back in the 1960s, back when we used radio a lot more than we do today for television communication, for radar. Back in the 60s, there were also even nuclear tests that were emitting radio wave radiation sufficiently powerful to escape our atmosphere. All of these are indicators of an intelligent, or at least partly intelligent, civilization. And if we think about how far those radio signals have traveled out into the universe, we can imagine a sphere centered on the sun that's about 80 some odd light years in radius. So if we think about the strongest radio signals that Earth has emitted out into space, they started back in sort of the late 30s. So we do the math, about 85 years ago is when we started becoming, we might say in astronomy, radio bright in terms of radio emission. And so we use that as the radius of our sphere in terms of the distance that signal has traveled out into space. Sorry about that. I seem to have an audio issue. So this perspective on our what we call our radiosphere, this representation of how far our radio signals have traveled out into space, gives us a sense of how many of these worlds could potentially have heard from us. So I'm not exactly sure where I cut off, but basically, if you're an intelligent radio astronomer residing on one of these planets inside the sphere, and you pointed your radio telescope back at Earth, you would potentially be able to detect signs of intelligent life. But if you resided on one of these planets outside the sphere, then you're simply too far away for our radio signals to have reached you. So this is an interesting kind of representation. If those spacecraft that I showed you earlier, those 5 fastest nuts and bolts objects that we've sent out into space, if that indicates sort of our sort of physical footprint in the universe, this is kind of like our electromagnetic footprint in the universe. So I'm going to go ahead and fade down the extrasolar planets, exoplanets, planets around other stars, and I'm going to kind of keep up our radiosphere as we now travel through the thousands of stars, tens of thousands of stars, hundreds of thousands of stars in our database. These are actual locations of these stars with appropriate brightnesses assigned to them. And as we pull farther and farther away from our radiosphere, it'll shrink to a circle and finally to a point. And now we'll get a different perspective on our Milky Way galaxy. We saw it from the inside and it looked like a hazy band that crossed through our sky. But instead, we now know that our Milky Way is a spiral galaxy. And the center of our galaxy is about 35,000 light years from where we are. The diameter of the galaxy is perhaps 100,000 light years. So this sort of city of stars in which we live that has hundreds of billions of stars, and also that gas and dust that blocks the distant starlight to form the lanes that crisscross through our Milky Way as seen from Earth. This Milky Way galaxy is an enormous collection of stars that represents sort of our gravitationally bound city in the universe around us. And off to the right, you can actually see this small and large Magellanic Clouds. If you ever have a chance to travel to the southern hemisphere, you'll be able to get a good view of those in the sky, much like pretty much anywhere on Earth with the dark sky, you can see the Milky Way. These two satellite galaxies of the Milky Way are actually interacting with us and sort of in orbit around us, and potentially disrupting our spiral arms over time. But what I wanted to mention here are these kind of red dots in the distance. Those are actually not stars anymore. We've traveled so far away from our home planet Earth, now hundreds of thousands of light years from home, so the distance that light travels in 100,000 years. Now we're actually looking at locations of other galaxies. So every one of those points represents an individual galaxy. Perhaps most of them are smaller, but perhaps as big as the Milky Way. Some are even larger. And if you think about that, that's kind of incredible. The distance across the Milky Way, again, I mentioned, is about 100,000 light years. If you think about where humans were 100,000 years ago, we hadn't even left Africa yet. And then that radiosphere, remember, way down here, you can still see it, again, sort of in the center of the screen. Well, that's sort of like our technological history of Earth in terms of our period of time when we've been creating radio emissions that are bright enough to escape our ionosphere, strong enough to escape our ionosphere. That's sort of Earth's technological history superimposed on human history, that diameter of the Milky Way. Again, using light, the fastest thing in the universe, is kind of a yardstick to measure these distances. So as we pull far enough away here, we'll leave our Milky Way galaxy behind, as well as these individual points that represent other nearby galaxies. There are about 30,000 galaxies in the data set that we're showing relatively close to home. This represents the work of dozens of astronomers working over a period of decades to make these measurements. And what I want to point out is that the galaxies aren't sort of uniformly distributed in space. Instead, they sort of clump and cluster together. In fact, there's a nice cluster here, the Virgo cluster, which is actually part of a larger structure that we call a supercluster, because astronomers are great at naming things. And these clumps and clusters of galaxies are a fundamental aspect of how our universe seems to be put together. And we see this pattern continue as we travel farther and farther from home. So again, this is a data set, 30,000 some odd points, dozens of astronomers working over a period of decades. We're going to fade up some other surveys now and finally make our way out to what's called the Sloan Digital Sky Survey, which is one of the most complete surveys of the universe around us. And now we kind of come back to this idea of the incompleteness of the data, as we would say. I pointed it out at Earth when we could see that seam between two images of Earth's surface, where you could see a seam between the cloud layers. Here, it kind of looks like the universe, although we've rotated away from it a bit, is shaped a bit like a bow tie. I apologize. I think I'm traveling so quickly here that we might be kind of losing our streaming speed here. But the try to move slowly enough here around the sort of central point, which is us, because we're, which I'll get to in a minute, kind of drawing ourselves at the center of this three-dimensional image. But the regions where we don't see many galaxies, and let me try to turn us around to a perspective where this is more clear. The kind of the gaps in the bow tie image. I apologize for the choppiness here. Let's try to get to a perspective and we'll slow things down again. So the absence of points that you see here at the top, kind of this wedge shape at the top of the image and here at the bottom. The absence of points there is not that there are no no galaxies in that part of the universe. It's just that we haven't finished making the map. So there's a gap, sort of incompleteness to our map that we're showing. Although we're showing you the locations of about 1 million galaxies, it's still a work in progress. So we're going to continue to fill in these gaps and learn where more and more of these galaxies are. Someone was asking, does this data set have James Webb data in it? And that's a great question. JWST is a telescope that's designed to look at a very small part of the sky with unprecedented resolution and fidelity. These surveys work a little differently. So the Sloan Digital Sky Survey, you're looking at broad swaths of the sky night after night in order to come up with the most robust measurement of the distances to these many, many points. JWST kind of zeroes in, and you can imagine it's kind of like a pencil beam in this representation, a single sort of line of sight out into the universe, and in fact is looking at galaxies very, very far from home. So, for example, let's pull this back a little bit farther, and unfortunately, I can't tell you exactly where it is, but I'll try to describe kind of what JWST sees. Again, if you think of that sort of pencil beam, we're pulling back far enough away now that we're seeing these kind of points that are fading up on the left and right-hand side are actually not even individual galaxies, but the bright cores of young galaxies. So bright, they're not like any of the galaxies that we see nearby, but very unusual galaxies indeed. And that's where we kind of confront a final idea, and this will cue up that question about JWST, because now we have to confront this sort of cosmic yardstick that I mentioned earlier. We've traveled so far from home. We're now billions of light years from home. And we have to confront the fact that light travels at a finite speed, which means that when we look out into space, we're also looking back in time. So the reason we see these objects, which are called quasars, far from home and not nearby, is because we're seeing the universe in an earlier state. We're seeing the universe as it used to look, as it used to look like. And this is sort of a terrifying concept, and yet something that allows us to tease apart the history of our universe in a way that we couldn't do in any other way. So looking out into space is looking back into time, and that's where the power of JWST is. You may remember, and I think I can bring this up, very early on, there was a release of the JWST, what we call Deep Field, and this showed individual galaxies, the bright objects that have these sort of six-pointed, or really eight-pointed sort of features are actually nearby stars. They're kind of photobombing this appearance of the more distant galaxies. So these guys are stars, but the sort of more hazy objects you can see here are individual galaxies. This one actually even looks a little bit like we think the Milky Way looks like. And then this sort of stretched images are actually galaxies that are even farther away, so we're looking at one of those clusters of galaxies like the Virgo cluster, and the more distant galaxies are actually having their light warped by the material in the cluster of galaxies. So this is a way to study extremely distant objects. But again, this is a little tiny pencil beam. There are many more galaxies here than would appear in that same section of the sky for our Sloan Digital Sky Survey data set. But we can study them in much greater detail. And that's the true power of JWST. It's looking farther into the universe, but in a very kind of narrow and sort of focused way. Well, that brings us almost to the end of the program. I just want to mention one more thing before we head home. I'm going to try to kind of keep moving slowly enough so it doesn't look too messy on screen. So I'm going to pull farther and farther from home and eventually fade up what is the punchline to the idea that light, looking out into space, is looking back into time. And that is, as we travel through all of these quasars very, very far from home, we'll eventually get to a point where we can fade up the cosmic microwave background. It kind of fades into our galaxy appearance here. Let's get a little farther back. But this sort of mottled, kind of dark orange to white, sort of textured pattern that you see in the background is essentially a baby picture of the universe. What we're seeing is the universe as it was perhaps less than 500,000 years after the universe started in the Big Bang. We're seeing the universe as it was very, very early on in its history. And unlike the image of the galaxy or the image of Earth that we showed you, the appearance of the microwave background is a little different. This is a very high contrast image. And so the dark parts of this, actually it's more like a temperature map. We're measuring the temperature of the very early universe. The dark parts are the coolest parts. The bright parts are the hottest. But that's a very tiny variation. The bright parts are only 1 part in 100,000 times warmer than the cool parts and vice versa. So what's interesting is that difference in temperature also corresponds to a difference in density. So the dark regions are actually quite a bit denser than the bright regions, but again, only by that tiny variation, about 1 part in 100,000. And so that variation, that tiny fluctuation in the distribution of matter in the early universe actually led to the clumps and clusters of galaxies that we see close to home. Before we go home, I just want to mention one last thing, and that is that the way we've been showing everything is that it looks like we are, the way we're drawing this picture, at the center of the universe. And that's a little deceptive. We're at the center of this 3-dimensional map that we've been drawing because we're the ones collecting the data. So we're simply mapping the distance of all of these objects relative to our location. So it looks like we're in the center of the universe, but in fact, the universe doesn't have a center. We're just at the center of this map of the universe, and the here and the now at the center of our 3D representation of the universe around us. So with that, I can't go too quickly, but let's go ahead and start heading home. As we do, that cosmic microwave background, that baby picture of the universe, will begin to fade down. As it does, we'll see in greater contrast the locations of the galaxies in the Sloan Digital Sky Survey, with the quasars more distant, same telescopes making the measurement, but observing objects that are much farther away. So these hundreds of thousands, nearly 1 million points representing the locations of individual galaxies are the most extensive survey we've made of the universe around us. And as we continue to fly into the center of our map, where Earth is, we'll pass by these distant galaxies and we'll once again approach the 30,000 some odd galaxies in our local map of the universe. The Sloan Digital Sky Survey is a mapping effort that was done rather quickly with a small number of telescopes. the data set that we're coming into now with these 30,000 galaxies relatively close to home is the work, again, of dozens of astronomers working over a period of decades. Virgo clusters are disappearing in the lower right there in our image, every one of these points representing an individual galaxy. But as we get close enough to our Milky Way, it will resolve into an image a little different from this undifferentiated dots that we see otherwise. We'll begin to see locations of the satellite galaxies of our own galaxy, like the Large and Small Magellanic Clouds that I mentioned earlier. Our own spiral galaxy. We left our radiosphere here in the center of our image. We'll pass through the thousands of stars relatively close to home, most of which have planets in orbit around them. As we pass inside the radiosphere, let me just take a moment to turn it off as we continue drifting home. And these many, many stars in our data set, again, each one represented correctly with its brightness and its distance to Earth, obscure the importance of the one star, kind of at the center of our image, our own sun, the location of our solar system. So we'll now do exactly the opposite of what we did before. We'll dim the sun to reveal the most distant nuts and bolts objects we've sent out in the universe, those 5 spacecraft, Voyager, Pioneer, and New Horizons spacecraft that we mentioned earlier. So we fade those lines down. We're left with our orbits of the planets around the sun. And we'll make our way toward the third rock from the sun, our own home planet, Earth. I want to thank you for being such a great audience. I couldn't see your faces or hear your murmuring like we would in the real Morrison Planetarium, but it was great to be able to share some of this awesome data with you. Again, this is software that we're using to show our virtual model of the universe. It's called OpenSpace. We'll be sharing a survey with you, as well as a link if you want to download OpenSpace and run it for yourself. You can do that. But the software is actually supported in part by NASA, and we're interested to know what you thought of today's program and to get some feedback on some of the things that we're doing with this free open source software. So with that, we'll end here with our view of Earth. Once again, seeing that the data is sort of incomplete as we look back at our home planet. This big missing chunk here in the Eastern Pacific is just data that hasn't arrived from the satellite in orbit around Earth yet. A reminder that this is data-driven representations of the universe around us, revealing the way that we observe the cosmos using our instruments here on Earth and out into space. So again, thanks very much for joining us today, and we hope you have a great afternoon. Thank you for taking part in our tour of the universe.